Thanks very much, Kenton, and thanks to the organizers for having me here. You know, I think I would put down the reason that I got into this field of quantum information as being the opportunity to work with Andrew Steen and the ideas he had on error correction. I am an experimentalist, but somehow trying to realize these goals seemed like a wonderful thing to have a go at, and so we're sort of hopefully I can convince you we're at the start of trying to explore those things today, and I'm excited to see how this progresses, and it's nice to see ongoing theory in this area. So indeed, the main focus of my talk will be on trying to encode a logical qubit, so just a single qubit in this case, in the oscillation of a single trapped ion, which is a continuous variable system, a bosonic system if you like, and offers an extended Hilbert space with the flexibility then to store information, but also to check things like stabilizer operators on that information without destroying the qubit. So the particular encoding I'm going to talk about is this beautiful idea that I think has been talked about plenty today by Gottesman, Kitaev, and Preskel. But from an experimentalist point of view, it's worth me starting by saying why are we interested in pursuing these sort of oscillator codes? And I think I would say in general, I'm not stuck on doing oscillator codes, but I rather pursue doing many types of codes in our trapped ion systems. And indeed, some of the things that we've been doing in the last couple of years have been to do with realizing error correction codes in qubit systems. And in particular, we're part of a collaboration as part of this IARPA logic program, along with the University of Innsbruck, with Sydney, Swansea, an Oxford theory team, and Mainz, in trying to realize an error correction code actually which would be encoded in 7 trapped ions. That's a Steen code, but it's actually also the base unit of these topological color codes, if you like. So the system there will eventually be 7 ions plus 3 ancillas. And one of the results that we had in the last few years was the main thing you're going to do here is go looking for stabilizer operators and checking their value. And so one of the things we were doing is just taking the smallest instance of that. We've got 2 qubits, if you like, and we can now repeatedly check the value of XX and ZZ stabilizers on those 2 qubits. And we can't just check them, because the other thing you need to do, as you all know, in quantum error correction is do feedback, i.e. if you find that the answer is the wrong one, that an error might occur, you have to be able to correct it with real-time feedback. And so here's just an example of measurements we were making where we were just stabilizing a ZZ stabilizer, if you like. So what we find, there's 50 cycles of measurement along the bottom here. And if we repeatedly apply these measurements, then what we see is that the value of the operator, if you like, decays quickly. But if we close the loop and apply correction operations, we can see that we stabilize the level of this thing to some degree, primarily limited by actually leakage in the hyperfine states of our qubit. So this was, I would say, a tough experiment for us to do. Okay, it involved controlling both beryllium and calcium ions simultaneously and doing 3 qubit gates and then also doing the feedback. But when we look forward, what is really needed for doing an error correction code? Of course, what we have to do there is wait for stabilizer operators, and we have to repeat 6 of them in order to make measurements of the syndrome before we do the feedback. And so we've been planning that along with the other teams, and just to give you an idea of one of the sketches that Marcus Muller, Alejandro Bermudez et al. Made for doing this, this is sort of some scheduling of tasks that would go on in an ion trap quantum computer in order to do this 7 qubit code. And it involves every one of these dots, or each line here is a time step, if you like. And what you see, each of these dots is an ion, and there are the whatever operations going on at that time step coming down the right-hand side, and then occasionally these ions get transported from one block to the other. But the main thing to take home from that is that it's pretty complicated, right? So it still looks a very challenging task. We think we have it in hand, but nevertheless a very challenging task to explore error correction in the context of multiple physical qubits, which in our case are multiple physical ions. And I think that generalizes for anybody who's working on qubit systems today. So it's nice then to think about whether you can't access things like error correction codes in systems which are simpler to control. Yeah, and I think the oscillator is a prime example of a system where you can have a single physical system, but you have a large enough Hilbert space that you have the possibility to control an error correction code and think about how to control it. And I should just say that I'm going to tell you all about work in trapped ion oscillators, but there's a complementary system. Rod Shulkoff has a series of beautiful results, he and Michel Devereux, I should say, in bosonic modes of microwave cavities. Yeah? And really what we do is fairly complementary to the things that they've been doing in that setup. Yeah. So what's the basic idea of the GKP code? I think probably I'm going to talk to a bunch of people who know this better than me, but let me give you my naive experimentalist's description of this. Somehow the proposal is down to these three physicists, if you like, but we found it interesting as we were working on this to actually find sort of discussions that were close to the sort of measurements that you make in these codes in John von Neumann's book, actually, on quantum mechanics. So he was looking for operators which are close to position and momentum, but which commute with each other, and that's kind of a key feature of these codes. So what's the key to this thing? It's an oscillator, and the oscillator, the main operator we consider on the oscillator is the displacement operator in phase space. And that can be a displacement by two complex values, and the key thing is that in general that thing does not commute, right? And it doesn't commute because of this phase factor, which is a constant complex number, if you like, but it depends in some way on these two amplitudes. But I think the key thing of this code is really that this formula here tells me that if you choose specific values of beta and alpha, well, you can arrange the commutation relations for these operators. And in particular, if you choose that this combination here is equal to some multiple of pi, then you can find that you can arrange for the relevant displacements to commute with each other. And in a similar way, a different choice will give you a value that's half of pi, and that can allow you to choose that these things anti-commute with each other. Yeah? So this is sort of the framework, the sort of operator framework for how this GKP code is realized. So the GKP code then exactly works in terms of this discrete grid of displacements. And I've sort of drawn a discrete grid. Actually, this is one of the eigenstates sitting below here. But what this is a grid where you can look for which are the relevant displacements to arrange for this commutation relation to hold. And so what we find on these sort of grids is that or what these guys proved, if you like, was that X operations and Z operations were a displacement by a single unit of the grid, and Y actually a diagonal single unit of the grid. And if you then choose the distances, this distance and this distance correctly, then you can arrange for anti-commutation between the two displacements. Yeah, and that's the right sort of rules that you need for the Pauli operators. Then what do you need for stabilizers? Well, you need a set of operators which would commute with all of these so that they don't disturb your logical information. And so what did I just tell you? I told you you can arrange for this thing to be m pi over 2, and that will give you things that anti-commute. So then it's pretty clear that if I want to make something that's twice as big, then I will then get a phase here which allows me to commute. And indeed, that's what the stabilizers are in this sort of code. They're displacements by 2 units of the grid. And one thing that I find kind of intriguing about this whole thing is you can stretch the whole grid horizontally, but then you have to squeeze it down vertically and vice versa. You've got quite a lot of freedom actually in how this grid looks. It doesn't have to look like a square grid necessarily. So what are we going to have to do if we're going to be implementing qubits on these sort of things? Well, one thing we're going to have to be able to do is to do measurements of all of these operators. So one thing I have to tell you about is how we measure displacement operators, or something similar to displacement operators. Yeah? So, but firstly, and it'll sort of be the final comment I make about this, so what are the errors that this code corrects? Well, this code corrects displacement errors themselves. Okay, so any displacement that's within a certain locality, if you like, if I took this grid and displaced it by some region but not too far, then I can correct that error. And what's that distance? Well, you definitely shouldn't have that this grid moves over by one cycle. That would be a clear logical error. But in fact, the fraction, there's a fractional level that you can pick, if you like, which would tell you what's the limit to the displacements you can tolerate in this code. And I think what's interesting about that is that many errors that you might have happen in an oscillator, which you might not think are just small displacements in phase space, actually to lowest order are just small displacements in phase space. So if you're somebody who deals with the microwave cavities, you'll find that photon loss is actually something which to lowest order comes in as a displacement in the phase space. So it's a very powerful code, and in fact was found recently by, I think, Liang Jiang's group to be more powerful than some of the codes that were specific specifically, for instance, designed for photon loss. So that was kind of an interesting result, I think, that came out more recently. So what do we have to do to make code states? Well, we have to make eigenstates of these displacement operators, right? And that's sort of the game that we're in. And the ideal way to do that then is to make really the grid that I showed you on the previous page. But if I just look in the x basis, that would be an infinite series, if you like, of evenly spaced delta functions in position, okay? And the one, that's the 0 state, if you like. The 1 state is then the same thing, but with this whole comb shifted along by half a period. So that's all very well and good, but that's a theoretical concept, and I'm an experimentalist. Unfortunately, the original theorists were also wise enough to spot that this was not a physically realizable thing, right? So they came up with something that we could attempt to make in the laboratory. And so an approximation to these sort of infinite comb delta peaks, if you like, is to take a Gaussian weighted distribution of then Gaussian peaks themselves. So in fact, this would be a superposition of 5 squeeze states with relative amplitudes meeting the Gaussian superposition, if you like, yeah? So this is the sort of thing that you might have to do, and in fact, when you do that in the laboratory, what you can think about, here's just a superposition that I've drawn of 3 squeeze states positioned at these positions here, and they've all got a relative amplitude, which I think this one is twice the amplitude of the outer ones in this case, yeah? And so then when you look at the Wigner function underlying a superposition of 3 squeeze states like this, what you actually are dominated by is a visualization of all the interference terms between these different wave packets, yeah? And that forms this nice grid-like structure on the phase space, which is the thing that I showed you earlier, but with this Gaussian envelope, which is an approximation then to the real code words, right? And the approximation will be something that limits the ability to do error correction. It invokes an error whenever you measure stabilizers and things, but if this approximation were good enough, and it's not yet in our case, yeah, then you should be able to cope with that error in doing the correction. Yeah? So how do we then measure displacement operators, and how do we build these code words? Well, one, I've sort of told you how we're going to build the code words. Well, if we can make squeeze states, then as long as we can make superpositions of different squeeze states, then we can make such approximations. Yeah? But for the measurement, what we do is a circuit like this. It's a common type of circuit, I think, for anyone who does quantum error correction, right? There's an ancilla, which in our case is 2 internal states of the ion, okay? And the system that we're trying to measure is the oscillator. So those are coupled together. We can couple them together. They're not typically coupled together in free space, but if you shine a laser on, it has momentum, and it couples to the dipole moment of the atom, or the quadrupole moment in our case, and so it couples to both degrees of freedom simultaneously, and we can then use that to couple these systems together. So the circuit we have to do, right, we have to make an X eigenstate and then do this controlled displacement, rotate the qubit and make a measurement. But for us, actually, that turns into a particularly simple pulse, and it's one that all ion trappers are very happy using all the time. It's exactly what gets used for these Malmer-Sorensen gates that maybe Mike talked about yesterday. Yeah. So what does it involve? It actually involves taking a laser, putting 2 frequency components on it, and driving simultaneously with the 2 modulation sidebands, the first modulation sidebands of your spin flip transition in your atom. Yeah? And if we do that, then we exactly get an operation actually that includes all of this stuff together. Yeah? So in the X basis, it makes a state-dependent displacement. So the Hamiltonian for that, we call it a state-dependent force, right? Why do we call it that? Because you can think about this stuff of being in the brackets as being a position operator, yeah? And then you've got something that's proportional to position, that's a force in the Hamiltonian, and here's the state dependence, which is dependent on the internal states of the atom, yeah? So what this does, after some time, you turn it on for some time, and it implements a displacement operator, which is state-dependent, right? Notice the operator sitting inside that displacement operator. So now you measure the spin, and you can look at what those measurement statistics, what gives you the measurement statistics, if you like, and you find that it's the expectation value of some operator between your original oscillator states. Sorry, the psi os should be this psi in that's sitting here. And actually the operator in question here is just the real part of the displacement operator. So one thing that's then a little bit surprising is that the real part alone is good enough to do the GKP code, but it turns out that for the particular eigenstates we use, then the real part is a suitable thing to measure. Yeah. So, and what is this in practice? This is actually just an oscillatory function of position and momentum. And I think, so these were, I think somebody cited some papers from the 1960s that were talking about these modular functions of position and momentum. Yeah, and so this would be a measurement of a modular variable. And the thing that interested people who were thinking about foundations, I think, in the mid-60s was that if you choose particular two modular variables, then even if one just contains momentum and one contains position, that they can commute with each other, right? And that's somehow not intrinsically intuitive to us, though I'm sure we all did displacement operator computations at some point, yeah. Okay, so that's the basic measurement, and we get then the information that's relevant about this modular value of the oscillator. Oh, now my laser went bendy because of this screen. Okay, good. So what's the challenge in our experiment with implementing this, right? This is an experiment. There's always a problem hidden behind the door, so I'll tell you about it, right? So the internal states of our atom look something like this, and the ones that we are talking about when I talk about a spin or a qubit are this excited D5 half state and this ground S1 half state, and they're separated by a laser which is at 729 nanometers. That's about 400 terahertz. Yeah. And when we do detection, what we do is we turn on other lasers. What they do is they take the population in the ground state, they promote it to the excited state, at which point it decays again, and when it decays, it emits light in a random direction. Yeah? And we pick up those decays, and if, what's nice is that it decays generally back to here, and so we go up and down over here, and we get lots of photons out. And you see here an averaged image of all of those photons over a certain detection window. But the problem with that from the point of view of this error correction or the GKP state is that that's a horrible thing to happen because every time a photon comes out, it displaces the oscillator, yeah? And it does it in a random direction. So that basically shreds our oscillator state, yeah? So what do we have to do? But there is one situation, right? That's the case if we started in the ground state, but if we start in the excited state, then we just don't scatter any photons. They're not resonant with the laser. And so actually there you get an ideal result of a quantum measurement. You project back onto the system, but you don't get any scattering of photons, which then preserves the oscillator state. And so that we'd used previously, so we post-select then on a dark measurement, and we'd use that in order to make what's called Schrödinger cat states. So this is actually a picture, and you can think about this as being position and this being momentum. And here are two blobs, which are separated probabilities, if you like, to find the atom here and here, or amplitudes to find ourselves here and here. And here you see these interference fringes that pop up when you can see the coherence between the two blobs. So this is, I think, negative superposition of these two states. And just to say that this is really, this stuff here is what's going to become the interference pattern that builds the grid states in a certain sense. Yeah. So what do we do if we want to make three components? Well, we just take a two-component version like this, and we actually repeat the whole cycle. We apply this state-dependent displacement, we measure, we post-select, and then we project into some three-component superposition. And as long as we started in a squeeze state, then we start to get approximations to the GKP states. So here's just a couple of versions of this, right? So these are actually theoretical Wigner functions. You'll see experimental Wigner functions later, if you like. So this is one where we make 3 superposed squeeze states with a 2-to-1 ratio. This is one where we make 4 superposed squeeze states with an even ratio across the top. And so we can reconstruct, actually using these modular variable measurements, we can reconstruct in position what these eigenstates look like. This is really the blue is the measurement, if you like, the red is the theory, yeah? And we can also do that in the momentum space, and you see this nice periodic structure appearing in both position and momentum, and that's sort of indicative of the grid-like structure of these states. So what did I tell you? I told you that for measuring operators of these things, then we have to make these state-dependent displacements followed by a measurement, exactly the same as we did for the preparation protocol. Yeah? So what do we do? Well, we can start with a zero logical state. So you can imagine what the Wigner function for that is in our approximation, and you see that there's sort of grid-like structure in the middle, there's no grid-like structure on the outside, right? And you can think, what am I doing when I'm actually making this state-dependent displacement? So what am I doing? I've got an internal state, let's say it points left or right, and that state then becomes, as I displace, it becomes entangled with the oscillation state. I displaced my oscillation copy either this way or this way, dependent on what the internal state of the ion was. So what's going to happen as a function of displacement size if you do that in a grid-like state like this? Well, if these are two grids, right, and they start to separate, they'll stop overlapping with each other. And when they don't overlap with each other, you'll lose interference, right? So you'll see a change from being in a one state all the time to actually being in an entangled state with the spin, and you'll lose interference. But then at some time later, you'll displace far enough that these things overlap again, and then you see quantum interference again, right? So you should expect to then see a revival in the signal as a function of this displacement amplitude. Yeah? So let's do that in the vertical direction and see what we see. Indeed, what we see as we pull this thing apart, this grid-like structure apart, is that we see drops, and that's when these grid structures stop interfering, but then we see revivals when these things overlap again. Yeah? And we see, in this case, 1, 2, 3, even maybe a small revival sitting over here. So that's for the zero logical state, and indeed what we can do then is we can say that these first two revivals are relevant things for this particular code. This one is actually the readout of the Z operator, which goes up towards 1, and this one's the measurement of the stabilizer operator in this case. So I'll just say one more thing before going back and looking at the details of that plot. So here's the case where we've provided the one logical state, if you like. So what is that? That's shifted by 1 unit to the right. Yeah, and we make the same measurement, the state-dependent force in this vertical or P direction. What do we see there? We see the same thing, collapses and revivals, except that that first revival goes in the opposite direction, right? And why does it go in the opposite direction? Well, because this is the other eigenstate, and this is now my Z operator. So here I'm getting a negative value for my Z operator. Here I have a positive value, yeah? And those are the two qubit states for this eigenstate measurement in the Z basis. And then what do you see at the distance relevant to the stabilizer? You see that it goes back up again, and that, of course, is exactly what you want. You want that the stabilizer has the same value independent of which of the logical states that you're in, yeah? So what can I say about this? Remember that these are finite states. They've got this Gaussian envelope, and so they're only approximations to these nice GKP states, right? And so the red curve actually gives you the ideal theory for the states that we are making, the finite size of states that we are making. And what that sort of tells you is that probably we can't do error correction in a serious way yet, yeah? Because these stabilizers are sort of on the 60% level rather than, or even ideally are up in the 60% level rather than going up to 1. But nevertheless, we see then the structure coming out of these underlying states, which is kind of nice, yeah? So the other thing we can do is we can do that in all dimensions. So here's a case of a Y eigenstate. Again, this is theory, but then we have to apply our displacement operator along a different direction. So we choose the phase of our lasers to be correct for that. And again, we see similar sort of structure for this Y eigenstate. And here now is a joint stabilizer, actually, of both Z and X. This is the Y stabilizer, if you like, sitting here, yeah. So we do that over the whole block sphere, and I think rather sort of surprisingly, in a certain sense, we get fidelities that are on the sort of 88% level for all of the, so producing all of the different eigenstates of the block sphere and also making the measurements on those. So the combination of all of these measurements, of course, allows you to do tomography in a fairly straightforward manner, yeah, so we directly measure that. Okay, so then that's a logical qubit, and we seem to have indications that we can make all of these principal states, but then along with that, you'd like to be able to do operations on these qubits, right? So the nice thing, at least for the Pauli gates, is that this is just for displacements in phase space by a discrete integer number of this grid, right? So how do we do that? It's actually a little bit different. We just apply an oscillating voltage to a trap electrode, and that actually just displaces the ion for a finite amount of time. So we can look at, we do then process tomography on that. We characterize it with these process matrices. And what we see for these Pauli gates is that this oscillating drive is really easy to control for us, actually. It's sort of one of the nice things about this GKP code, I think, is that the states are sort of reputedly hard to make, and indeed reasonably hard to make for us too, but the operations are quite simple. Yeah, and these are these displacement operations that we can do quite well compared to anything else that we do. Yeah. So that's sort of Pauli gates, of course. You'd like to be able to do more than that. In fact, one gate is the Hadamard, but for us that's sort of just you could sit in the background and just change which phase you choose for your X and Z operations, so that's sort of rather uninteresting to us. But the other thing we'd like to be able to do is universal rotations. And there we go to this sort of standard trick of doing gate teleportation operations. So the deal there is that we can apply arbitrary rotations rather easily to our internal state qubit, but it's much harder to do to this GKP code. Yeah? But the nice thing is that this teleportation circuit really only requires doing, again, state-dependent displacements, just what we were doing for measurement and state preparation onto the qubit state. And all we have to do is add to that whole circuit this little rotation that happens on the internal states. So what does that do? That implements conditional, of course, on this state here. Yeah. Then it implements some unitary transformation, or so I should say some operator, yeah, which is not necessarily unitary, right? But has this, depending on the settings, if this is a controlled X operation, or we chose the direction relevant to X, then you see it's like a phase gate in the X basis. Yeah. And so what do we have to do in order to make a unitary operation out of that? We have to choose that theta is equal to pi by 2, and then we get just a phase shift rather than any change in the amplitudes. And here's a case where we've scanned then the phase that we're using for this operation while keeping theta fixed. And you see nicely that this is a rotation about the x-axis, right? It changes the y and z eigenstates in an oscillatory fashion. And the x, well, it changes a little bit. That's probably a slight miscalibration, yeah? But nevertheless, it doesn't vary very much, yeah? So what we see is that in that context, then we can achieve universal control, if you like, of this qubit, because we can tune these different sets of gates to build up any operation that we like. And of course, the sort of, so I should just mention that choosing theta not equal to pi by 2 actually allows us to do non-unitary operations, and I think that's something where we should think about what that might be useful for in general. Yeah, that's something that's down the line for us. Yeah. So of course, one of the classic non-Clifford gates is to do this T gate, this pi by 4 operation. So again, here I'm showing this chi matrix that somehow characterizes the process that goes on. And this is the case of the ideal theory, and what we find in the experiment is something that looks pretty similar. And then let me just quote a fidelity. So we find for these teleported gates that typically the process fidelities are not as high as for just straight displacements, but nevertheless we got sort of 90% or more fidelities, which I think compares well with anyone doing logical qubits in multiple spins or something like that, right? That sort of is the relational challenge of these two architectures, right? The oscillator is somehow easier to manipulate. So I'm going to summarize and give an outlook. That's not quite the end of my talk, so Ken shouldn't get too excited. Yeah. So what have we been able to do? We've been able to make and reconstruct and control these logical states of this trapped ion oscillator. In fact, the reconstruction, and this is really a Wigner function that we're able to extract now from our experimental data, is based on using these modular variable measurements, which just pull out the characteristic function of the oscillator in a very nice and clean way. Yeah? So actually, that's been able to speed up our data acquisition of these sort of states by a factor of 20 or so. That's really a powerful technique for us. The other thing that we're keen to sort of look at, and we're starting to look at now in the lab, is the fact that these states are sharp, if you like, in 2 dimensions simultaneously, and you have operators that you can measure in those 2 dimensions which commute with each other, right? So which can be simultaneously recorded. And so this is a prediction from Barbara Terhal's group that these would be useful for precision measurement. And for instance, our state GKP states are sort of squeezed by 7 or 6 dB around in both dimensions in this case. So we're trying to use that for Bayesian sort of measurements of the small displacements. I should say there's a whole stack of other things we'd like to do. One of the things we'd like to do is to do error correction, though for us at the moment this destructive nature of one of the readout options is really a problem for us conceptually in thinking how to do error correction. One thing you might think is to do autonomous error correction, and there we have to make a few estimates about recoil to see if that's possible. But one way that would really be the future, if you like, is to use a multi-ion system. So take one ion, it oscillates, and it resonantly then couples to neighboring ions if you can put them in the same trap. So you can transfer information between 2 separate oscillators. And in fact, if you think about making a quantum computer on the GKP sort of code, if you like, it does rely on using this as a base element doing the continuous variable correction here, and then using this as a qubit embedded in a much larger lattice of codes. Yeah? And so there you get back to the same old problem we have with trapped ions of thinking how to make big lattices of trapped ions. And I think that's really one major headache for us looking forward in the field. Yeah? So let me tell you my little story on that, and then Ken can contradict it whenever he wants. Yeah. So the deal that I see is that trapped ions, it's challenging to go into 2 dimensions. Yeah. And the reason it's challenging to go into 2 dimensions is that you have a combination of a static and an RF potential. But Laplace's equation tells you that an RF potential can only have an electric field of 0 along a line. Yeah. That's just a fundamental result. Yeah? So you'll see that trapped ion people are very happy and produce beautiful results along lines, right? Chris Monroe and Rainer Blatt have done beautiful experiments for many years along these lines, and of course others. Yeah? But there's also other problems this RF potential causes. I think one that's particularly keenly recognized at present is that it heats up chips, which are starting to put all of these as chip structures in cryostats, and then this heating is a problem. But also, I think if you talk to students, they would say that the co-alignment of the radio frequency, microscopic radio frequency potential and the static potential is a daily task that they do in the lab, and it drifts and they don't know why, and this is sort of all a pain to deal with. Yeah? So one of the ways to then overcome this line, if you like, came up with from Dave Wineland, right? So one of these ideas was to have sort of segment chips with segmented electrodes and then try and push ions through these 2D junctions. And I think what any of us find is that when you go through those junctions, you're going to have large driven radio frequency motion. And that's something that is dealable with, so people have been through these junctions with almost no excitations, which is exactly what you'd want for quantum computing, but it makes you very sensitive. And this is something that I think we should not have to deal with, is being very sensitive to every parameter that we use, right? We have enough problems in quantum computing without making them for ourselves. Yeah? So how can we overcome this problem of the RF potential? And in a sense, then, a path is shown by beautiful work that's being done, I think most of the NIST results, but there are newer there are older groups doing nice stuff, and there are newer groups. Mike Bierczak has a nice penning trap experiment. So here you would see pictures of hundreds of ions in a plane, right? This is exactly such a picture. And you see that it's got a nice structured lattice, if you like. But this is really a bulk system, right? It's got a few constraints, right? It's a bulk system, so your lattice is fixed to whatever physics gives you, if you like. And it rotates at 60 kilohertz, actually. So it's not something where you think, I can just use this for quantum computing. And furthermore, if you think about scaling this to, what do we need, 100,000 qubits, Ryan told us the other day, I think that's just not on the agenda, right? So how can we take advantage of this in our own work? And that's where we've been thinking. Okay, so the penning trap that I just showed you had a global big potential in which all the ions sat, yeah, which was added to a static magnetic field made from a big bulk magnet, right? So it sits in the bore, an 8-centimeter bore of a big superconducting magnet. So the nice thing about that, in the sense of, is that you replace your local RF field, which has all its problems, with a big bulk field, which comes from the magnet, okay? And now our new step, if you like, or I think a few people have sort of vaguely considered this, but I think we've taken it to its conclusion, is to now replace the global potential for all the ions by a single quadrupole potential for every single ion above a chip. Yeah, and the real, I think the new step there is to take advantage of microfabrication, which people are using readily with RF traps, but haven't really applied to penning traps, okay? So the challenges you can think of there are how to get ions close together, and so what you need is small electrode structures in order to make an individual potential for this ion and this ion, and then you ask the question, how close together can I get them? Because that tells you how strongly coupled this system is, yeah? And so I think we've been fairly pleased that for regular lattices, it seems like you can achieve, these distances here are the same distances that you see in the Bollinger continuous lattices, yeah, the bulk crystals. So that's fairly promising, but I actually think there's more promise than that. And that's to think about things like the surface code, right? And the difference between what you do for quantum simulation is, in quantum simulation, you might turn on a Hamiltonian for your whole set of qubits, right? And in something like quantum computation, you want to keep errors fairly local, right? So you want to isolate pairs of ions. And so the thought here really is that because you've got a lattice of electrodes that you can control independently, you can detune two of these ions from the rest of the array. And at that point, they're decoupled from the rest of the array, but they're coupled to each other. And so what we see in the numbers, so here's just a picture of the normal modes of this 90-ion system, if you like, and these flat lines are where there are actually bands, which are the bulk system, but then there are 2 normal modes up here and 4 normal modes down here, which are just the normal modes of these center 2 ions that I've plucked out and tuned into resonance with each other. And what we see in simulations is that with Rabi frequencies that people commonly use in the lab today, it should be possible to do local gates with sort of 20 microsecond gate times on 2-qubit gates. So I think that's pretty encouraging, if you like, for trying this out. And we haven't even trapped in these structures yet, but I think this is now a promising angle. And I think that if I think long term, then what is this providing? It's really a 2D array of fairly static potentials, maybe sometimes being tuned in and out of resonance with the bulk, if you like. But what you do, if you quickly look at the sort of numbers for distances that I have here, you see that a 1 centimeter squared chip could hold Ryan's 100,000 ions that he needs to do a real computation. Yeah, so I think it's certainly something that we should consider exploring for trying to scale these systems up. So with that, then, I'd like to thank you for your attention. I'd also like to thank the people who are involved in the work. I've sort of cited the red people here are not quite the sort of full set, but I think for the GKP work, this was primarily done by these 4 people. But especially I should point out the contributions of Christa Fluman, who sort of took the whole modular variable thing and ran with it from Schrödinger cats onwards. She goes on then to join Rob Shulkoff actually in Yale, so she's going to continue bosonic, but she goes to the microwave side rather than the trapped ion side for now. Yeah, let's see if we get her back at some point. Yeah. So with that, then, thanks for your attention, and I look forward to any questions that you have. Yeah.
Great. Questions for Jonathan?
So the defect that you showed at the very end, is there a chance that you will operate not one defect at a time, but many in parallel, so that you would have parallel gates?
I think you could, yeah. This is just the first calculation I've done, yeah. So I think the deal is that the Coulomb couplings between ion modes fall off as 1 over d cubed. So it depends at what range you might try and do that, if you like. But I think you're not going to probably take this pair of ions and then this pair here or this pair here, but maybe if you're a few sites over, then you can easily have them not resonant with each other, but at the same time coupled to each other, if you like. I think the one thing to say there is that the gate I'm considering here also is just the most simple gate you could think of. You just pluck the laser at a single frequency and drive, and there's some very nice structure of Penning-type modes which helps you a lot, actually. But there are more complex gates with multiple pulses, which are the sort of games people play on these linear strings, and I think that could help you do more things in parallel. Yeah.
Jonathan, could you say a little bit about like how this compares to, say, like Tobias Schatz's idea of RF honeycomb traps?
Yeah. So I think let me clarify what Ken says. So this idea, in a certain sense, is not new for radio frequency traps, right? So many of us are focused on radio frequency traps, and people have thought to make microscopic arrays of electrodes and have ions at individual RF nulls, so not connected, so no 1D problem, but. So what's the challenge with that? The challenge is just getting these ions close enough together. And you lose hugely or you lose quite considerably, I would say, by needing to use RF. Because RF, you just need much higher voltages. So you get a 16 times higher curvature. With the sort of normal Q parameters we use, you get a 16 times higher curvature with the Penning trap than you get with the RF trap. So you can get these ions closer together, and your couplings will be what I would call reasonable, rather than, I find today the numbers somewhat unreasonable for what I think. Yeah. So, yeah.
Any other questions for Jonathan? Yeah, Mike? Wait for the microphone.
Thanks for a great talk, as always. Just on the last bit, the Penning trap arrays, I guess we've seen that with chip traps, we've really struggled with optical access, and so there are whole traps designed to reduce things back to a line in order to allow laser access. So are you envisioning having kind of holographic outcouplers and integrated photonics in order to do the addressing in these larger arrays?
So I think there are stages to this, right, as you know, sort of thing. I think in the quantum simulation, I would say that you could try and keep the array fairly small at the start and use bulk optics. I think we would start with beryllium ions, which are not so good for the integrated optics, yeah. Albeit that, maybe I can even illustrate it, the sort of thing Mike's asking about is that recently from MIT, and in fact we have results on this just come out of the lab in the last 2 weeks and we're on our poster yesterday, is these ideas of having then waveguides integrated with chips, where there's a diffractive grating essentially that focuses the beam down on the ion. And we are able to do that with calcium ions and in RF traps currently, but I think if you want to scale for a 2D lattice, like I actually think if you look at the numbers that I gave here, right, the spacing of this lattice is 30 microns, and that's actually quite a lot of space to fit things like grating couplers on. I think the other advantage of the penning trap is that any stray electric field, my expectation is that it just moves the center of the trap, and it doesn't lead to micromotion compensation. So we've had problems where the RF-driven motion doesn't coincide with where the beam comes out of the chip. And so I think in this context, you'd be free of that constraint. That's quite powerful.
All right, let's thank Jonathan again for a great talk.